Hello, my name is Liam Mosier. I'm a member of Group 3. For question 1, we were asked if we have a steel dagger, how we get a ductility larger than 15% and a tensile strength larger than 800 megapascals. For our thing, we wondered, could we go straight to 3 centimeter final diameter? We tried this by calculating it, and we found that if we did that, we would end up with a cold working of 64%. Looking at our chart, if we do 64%, while it would have the correct tensile strength of well over 1400, our ductility would be significantly too low at around 5%. So instead, we decided that we'd have to cold work first, then heat treat, then cold work again. So we decided to find the diameter we'd need after the first thing of cold working. To do this, we used our equation, which was this right here. We found it to solve for DO. And for DO, with our target cold working of 28%, which would get us both values as we need them, we ended up with an initial diameter of 3.536 centimeters. So, for our process with a steel dagger, first we were thinking cold work. And we will do that because we're going to reduce the diameter of the rod from 5 centimeters to 3.536 centimeters. This will change some of the material's properties. However, we will fix this using heat treating. This will bring it back to a pretty normal state. However, it will not change the diameter from 3.536 centimeters. Third, we're going to cold work it again. We're going to reduce the diameter to 3 centimeters. This will get us our target cold working percent of around 28%. This will also give it a tensile strength of around 1000 megapascals, so a little over. It will also give us the steel percent ductility of around 18%. So, how we got our formulas. We started with our percent cold working as the initial area minus the final area over the initial area. We can use this formula and replace area with the formula for an area of a circle, which is pi times diameter squared over 4. And now we replace that, we get this entire formula, which is right here. And from there, we can reduce this as this over this will equal 1, and this over this will eventually equal df squared over do squared. We can use this for our percent cold working instead of having to fill in for an area every time. For question 2, we were asked if we repeated the same process for an aluminum dagger as we did with a steel dagger, what would be the end result? So, as our process for steel, it was first cold working, then heat treating, then cold working again. So, for the aluminum, after the first set of cold working, the diameter would change from 5 to 3.536 centimeters, which is the same as our steel working, as this is a reduction in area, which would be the same as our cold working percentage. Heat treating would then restore the properties of the aluminum. Finally, as our third cold working, this would reduce the diameter of the rod to 3 centimeters. Same as our steel so far. However, our final tensile strength and our final ductility would be different, vastly. As you can see, for our aluminum sample, we get vastly different answers than we would do with our steel. Our goal for cold working was 28%. Here, we're 28%. Our ductility is only around 6%. At the same time, our tensile strength is only around 150 megapascals. This means our aluminum sample, compared to our steel sample, is much more brittle and less able to bend. It'll also be less able to flex, stretch, and have strain. This means it's much more likely to fracture and snap sooner than our steel sample. Lock in.
Hi, my name is Tyler Ehrlich, and I'm also part of Group 3. Today I'll be talking about the cold work hardening and how it affects both materials. As you already know, these two materials are steel and aluminum. The first material we'll start with is steel. After cold working, the steel becomes stronger, harder, and stiffer. However, cold working will also make the steel become brittle. The steel also needs to be annealed after cold working to soften it and relieve internal stress created by the cold working. Some examples of where we use cold work steel in real life are in bolts and screws, car body parts, and steel wires and cables. Now for aluminum. Aluminum also becomes stronger, but is still significantly less than steel, and becomes significantly more brittle compared to steel given the same cold working amount. Aluminum is lightweight compared to steel, and cold working helps add strength to it without adding any weight. Aluminum is also annealed sometimes, but is done at a much lower temperature than the steel due to aluminum's lower melting point. Lastly, some examples of where we use aluminum in the real world is in cooking foil, bicycle frames, and beverage cans.
Hello, my name is Andrew and I'm also in Group 3. There are several mechanisms through which cold working affects the microstructure of material. Some of these mechanisms are the disruption and/or distortion of grains, the reduction of average grain size, and lastly, the increase in the quantity of grain boundaries. These changes in the structure of the grains composing a material cause the defects and dislocations present in that material to have greater difficulty in translating through places in it, increasing its hardness, its resistance to distress, decreasing the material's ductility. Another form of heat treatment is annealing, which also significantly affects the microstructure of a material. The mechanisms by which annealing affects the structure of a material are related but different than the mechanisms involved in cold working. Like cold working, annealing changes the size and quantity of grains and grain boundaries, but unlike cold working, annealing involves the increase in the sizes of grains and thereby reduces the difficulty of defect translation through the material, causing the opposite effects of cold working, being a decrease in the material's hardness, its resistance to stress, and an increase in ductility. Annealing also has several stages in which it causes change in the material. The first of which is recovery, in which dislocations begin to annihilate oppositely aligned defects. The second is recrystallization, in which small new grains form with a reduced quantity of defects. And last is grain growth, in which the quantity of smaller grains shrinks and larger grains increase in size.
Here we will show him our work on how we found the diameter that we needed for the steel sample. So we have our formula here of the original area minus the final area over the original area. The area formula for a circle is equal to pi r squared. However, we're working in diameter, so we will change this to pi over d over 2 squared, which is equal to pi times d squared over 4. So we will use our original formula here, and we will change it to use our area formula. So our percent cold working will be equal to pi d squared over 4. This is our original diameter, which is the one we were looking for, minus pi df squared over 4, all over pi do squared over 4. However, as there's pi and divided by 4 in every single number here, we can change this to do squared minus df squared over do squared. We can change this to do squared over do squared minus df squared over do squared. This will then go to 1 minus df squared over do squared. This is our percent cold working. However, we are looking for this. So we will then solve for that. This will be equal to our cold working minus 1 equal our negative df squared over do squared. We will take the negative of each side, so 1 minus the cold working is equal to df squared over do squared. We can then multiply by do squared on each side and divide by 1 minus the cold working on each side. This will bring us to our DO squared equal to DF squared over 1 minus the cold working. And now you can take the square root of this to solve for DO. And that is how we solved for our diameter that we needed after the first cold working.